stop thinking of numbers as static dots. To truly understand the distribution of primes, we must view them as a compressible, viscous fluid. By bridging the gap between number theory and fluid dynamics, we see that cryptography isn't just abstract math, it's physics in motion. Today, we'll explore how treating numbers as dynamic flows can reveal the hidden structure of the prime numbers that secure our digital world. For centuries, we viewed the discrete world of number theory and the continuous world of fluid dynamics as entirely separate realities. On one side, we have the rigid jumps of integers. On the other, the smooth, swirling flows governed by Navier-Stokes. The arithmetic fluid dynamics framework bridges this gap. By treating the integer line as a physical medium, we can finally unify these domains, revealing a profound holographic connection between the Riemann zeta function and the mechanics of the continuum. Think of the number line not as empty space, but as a dense arithmetic vacuum. By mapping physical variables to number theory, we can view composite numbers as information density and pressure as the internal force resisting factorization. This isomorphism suggests that the integer line is a plenum, a space filled with matter, where mathematical operations are actually physical processes of decompressing information. While we often view primes as static building blocks, hydrodynamics offers a more radical perspective. Primes are shock singularities. Imagine the number line as a fluid flow, where arithmetic stress steadily accumulates. When that stress reaches a breaking point, we see a prime release event, a sudden explosion of mathematical tension. This Dirac-Combe model suggests that primes are essentially sonic booms in a supersonic flow, marking the exact moments where the underlying fabric of arithmetic suddenly snaps. Let's examine the golden Navier-Stokes equation, a theoretical bridge between fluid dynamics and the mathematical elegance of the golden ratio. By introducing phi as an eigenvalue of efficiency, we scale spatial and temporal derivatives for optimal flow. This approach maximizes irrationality to prevent shock crystallization, while the inherent fractal scaling ensures energy cascades perfectly across scales, governed by the unique properties of phi. Think of cryptographic security through the lens of fluid dynamics. By applying the concept of an arithmetic Reynolds number, we can visualize the transition from insecure, laminar math to secure, turbulent systems. While small numbers allow for trivial factorization, cryptographic scales, like 256-bit, create a regime of chaotic mixing. Ultimately, security isn't just about hard math. It's about operating in a high turbulent environment where calculation trajectories become irreversibly mixed. The Riemann zeta function acts as a spectral analyzer for a hypothetical arithmetic fluid, where its zeros represent resonant wave numbers. By framing the critical line as an axis of hydrodynamic stability, the Riemann hypothesis becomes a statement of physical balance. It suggests this fluid is inherently stable, never producing rogue waves or blow-up solutions away from that central axis. Ultimately, this perspective connects the distribution of prime numbers to the fundamental physics of resonance and stability. Imagine trying to track one specific water molecule inside a hurricane. That is the level of complexity we face when attempting to solve the discrete log problem. By treating the SECP256K1 elliptic curve as a boundary condition for arithmetic flow, we create a system of extreme mathematical turbulence. This mixing is so chaotic and irreversible that it provides the foundational security for modern cryptography, making the private key practically impossible to find. Think of digital security not as a locked door, but as a river of honey. This is the honey river paradox. Moving downstream represents multiplication. It's fast, low viscosity, and effortless synthesis. But for a hacker trying to swim upstream, that's factorization. It requires fighting against intense arithmetic friction. The irreducible overhead theorem suggests that security isn't just a math puzzle, it's a thermodynamic reality. The river is simply too thick to swim against. Think of Shor's algorithm not just as a faster codebreaker, but as a total phase transition in how we process information. While classical computing struggles against the friction of complex calculations, quantum computing operates like an inviscid superfluid. By eliminating this computational resistance, we enter a state of zero friction, where prime factorization becomes trivial. This arrow of arithmetic time represents a fundamental shift that renders our current cryptographic standards obsolete. Lemmer's gap represents a fundamental boundary in what we call the arrow of arithmetic time. While we often view quantum computation as a frictionless superfluid, Lemmer's conjecture introduces a critical computational friction that forces instability. As an algorithm passes through this narrow gap, the flow erupts into chaotic shockwaves and quantized vortices, effectively breaking the smooth efficiency of quantum attacks.